One method of measuring the hydraulic properties of soil in situ, in the field, is really worth looking at in a little more detail. We call that the instantaneous profile method. And it's a fairly simple setup. Basically, we go to a field, and at various positions, we put in tensiometers that measure the pressure, and we put in perhaps a neutron access tube, which allows us to measure the moisture content with depth. And so we're going to put in a number of these tensiometers and get the pressure at a series of depths. And we'll then have the moisture content at those same depths. So we'll measure it specifically perhaps at these 4 depths. Okay, so that's going to be our basic setup. The experimental conditions are that we're going to saturate the system by irrigating water onto it, and then we're going to stop all evaporation, and then we're going to watch it drain. So, what are we going to learn? Well, let's go ahead and draw a picture here, for example, of the moisture profile here. Okay, so on day 1, at the start of our experiment, what do we have? We have basically the entire site is at theta sat, okay? So it's all saturated. So this is going to be dry, and this is going to be saturated. So this is going to be day 1, okay? Now what happens from there? From there, the site is starting to drain, and so maybe on day 2, we have this curve. And so what we see then is this amount of water drained out of the soil profile. So that's the lost water. Where did that water go? Well, if we look at this depth, for example, we're going to say that the flux here is equal to the delta moisture content, the change in water content, if we add that all up, divided by 1 day. And so here we have the flux as a function of the changing water content in time. Interestingly, one of the things I really want to have you think about is that what's the flux here? Well, the flux here is exactly the same as the flux here because there was no further drainage, but all that water that drained out of here had to make it somewhere. So keep in mind that the flux is cumulative. So for example, the flux here was just equal to this delta theta 1, which just is this area here, okay, over the 1 day. So as we go down through the profile and we accumulate more and more of that drainage, the flux increases until it reaches the area where there's no further additional drainage, and so the flux is equal to whatever came from above. So now we have the flow, and we also here are measuring pressures. So at each of these elevations, we have a pressure. So we have this tensiometer, and so what we can get are pressures and water contents. So what we can do then is by mapping the pressure at that elevation in time, we can immediately get from saturation down the retention curve. So right away, we get the retention curve, water content versus pressure, for each elevation at which we have a tensiometer. But the other thing you have when you have a tensiometer is you have the pressure. And therefore, if you know the depth of this tensiometer, then we know that the total potential is just equal to the pressure potential plus the elevation potential. And so, by measuring the pressure with our tensiometers, we exactly have the total potential. Aha! We have the flow here, and the total potential, and we have the space between measurements of total potential, which means that in these gaps, we can estimate the gradient in total potential. And of course, when we have Q equals minus K del H, if we're measuring Q by looking at the time rate of change of moisture content, and we're measuring gradient in H, then we can solve for the unsaturated conductivity as the system drains. So this is a very simple experiment in a sense, where we saturate the profile, watch it drain in time, and in so doing we get the retention curves at each elevation as well as the unsaturated conductivity curve as it drains. The experiment typically takes a few weeks, but it is the most robust method we know of to get the in situ characteristics of a soil.